So yesterday we discussed about the Fermi surfaces and how the Fermi surface will fold in first Brillouin zone when we do the reduced zone scheming, and we saw that if we have a monovalent atom or monovalent metals, it means it will have only one electron. Its valence state would be +1. So like alkali metals, sodium, potassium, lithium, all, and they have the BCC structure. So we saw that how the Fermi surface will look like in the absence and presence of a periodic potential. Then we also considered the noble metals like gold, silver, and platinum and all that, which have the abscissa structure, and we also saw that how the Fermi surface will look like. And we concluded the lecture with the discussion on divalent atoms. So let me recapitulate it for you. In the case of divalent metals, the number of electrons is precisely enough to fill a single zone, means first Brillouin zone. And in the absence of periodic potential, the Fermi surface is still circular or spherical, although it now crosses into the second Brillouin zone. So this is the first Brillouin zone and the Fermi surface for a divalent atom. But since the two areas are equal, that's why the Fermi surface is extending into the second Brillouin zone. It is in the absence of any periodic potential. It is in the absence of periodic potential. If we apply or if we introduce or if we switch on a periodic potential of intermediate strength, then what is going to happen? We know that at the zone boundary, there will be appearance of a energy gap, and the energy levels which are very close to the zone boundary in the first Brillouin zone, their energy will get lowered, and the energy states which are in the second Brillouin zone, very close to the boundary between first and second Brillouin zone, their energy would get shifted up, and the electrons would prefer to go in the lower energy states. Therefore, more of the electrons would jump from the second Brillouin zone to the first Brillouin zone. So this is the diagram of a Fermi surface with the introduction of intermediate periodic potential. We can see that these states which are lying in the second Brillouin zone, some of the electrons, they jump from the second Brillouin zone to the first Brillouin zone to acquire the low energy state. So this is the diagram how the Fermi surface will look like for a divalent material under the influence of intermediate periodic potential. This is in the extended zone scheme. It is consisting of first Brillouin zone and second Brillouin zone. Now if we do the zone folding, means we translate the parts of the Fermi surface which lie in the second Brillouin zone, the picture will look like this. This is the part. If we translate it, it will appear here. If we translate it by a reciprocal lattice vector, it will come here, and the remaining parts will do like this. So this is the sections of Fermi surface lying in the second band, but now they have been shifted to the first Brillouin zone, and it is the reduced zone scheme. This picture is the same like this picture. It is under the influence of a intermediate strength periodic potential in which there would be a break in the energy levels of the starting of second Brillouin zone and at the end of first Brillouin zone, and most of the states which are lying in the first Brillouin zone but are close to the boundary, they will be occupied. So this picture shows the behavior of Fermi surface in the periodic zone scheme for a divalent atom under a divalent metal under the influence of a intermediate strength periodic potential. If we further increase the strength of the periodic potential, then all the electrons, the gap would be so much between the first Brillouin zone and the second Brillouin zone that all the electrons which are in the second Brillouin zone, they would prefer to occupy all the vacant states in the first Brillouin zone, and this way, under the influence of a strong periodic potential, the first Brillouin zone will be completely filled. It would be separated by a large energy gap from the second Brillouin zone. So these electrons cannot jump from the first Brillouin zone to the second Brillouin zone because there is a large energy gap. Therefore, two-dimensional material which was behaving as a metal under the influence of intermediate potential, it will become insulator. And this is the diagram which looks like for a two-dimensional insulator. You can see that this sky blue color, it shows, it fills the complete area, means all the electronic states lying in the first Brillouin zone are completely filled. That's why it is insulator. If we go to the polyvalent atoms like aluminium or higher group elements, so we see the Fermi surface becomes more complex. So for some of the polyvalent material, this is the shape of Fermi surface, and it is in no case similar to a spherical Fermi surface. So by now we have understanding that in reality the Fermi surface is not spherical in shape as proposed by Sommerfeld while discussing the quantum free electron theory, but under the influence of a periodic potential, the Fermi surface acquires a complex shape. We can also discuss the influence of electric field and magnetic field, or if we say simultaneously, the influence of electromagnetic field on this Fermi surface. So here the first diagram shows the Fermi surface in the first Brillouin zone, that is without electric field. So when we apply electric field, more the electron will move in the opposite direction of the electric field. Therefore, these states which are lying on the right hand side, they will start getting occupied. More and more states will on the right side will start occupying, and the states which are on the left side of the Brillouin zone, they will start getting vacated. Now you can see that for any k value on the right hand side, we may not find any k value on the left side. Therefore, we can say that on the application of electric field will generate electric current. In the diagram on the left side, if we have any k value on the right side, simultaneously we find a minus k value on the left side, but it is near the zone boundary. In the case of right figure where we apply electric field, we may not find the two opposite states lying at the same mode k value. Therefore, this will generate the electric current, and the material will conduct electricity. And the effect of magnetic field we can study simultaneously, and this is the equation of motion of charge carrier under the influence of electric field. We will derive this equation maybe today or in coming lectures. H cross dk over dt, the rate of change of wave vector of electron is equal to minus E V cross B, minus E V cross B. Now you see the two different scenarios here, two opposite scenarios here. If the Fermi surface is lying in the first Brillouin zone, it will get distorted around, it will get distorted, or its part which is very close to the Fermi surface will get distorted. So this portion has been distorted, this portion has been distorted, and this portion and this portion. So these portions of the Fermi surface have been distorted because of their proximity with the zone boundary. And if there is any electron, on this Fermi surface, so it will move like this. It will move like this because of this equation. No, V is in this direction, and you see the magnetic field is in the inward direction of this page. Therefore, V cross B, the force on the electron would be in this direction, So under the influence of this magnetic field, the electron is going to move on this surface like this. This is the scenario when the Fermi surface is in the first Brillouin zone. But again, you see the second image where the Fermi surface not only Fermi surface lies in the first Brillouin zone, but part of it lies in the second Brillouin zone also, and therefore it intersects with the zone boundary. And these states are empty, very close to in the corners of this square, and these are closer to the zone boundary. Here, see the motion. In this case, the electron is moving clockwise, but here the electron is moving like this. If we make a periodic zone scheme, the electron will move on the surface, but the motion is anti-clockwise. So here the electron behaves as if it is having a positive charge, and it is near the top of a band. It is deep inside the band, but here the picture is at the top of a band. And in the coming classes, we will see that if there is an electron in the bottom of the band, the electron will behave like an electron with positive effective mass, but at the top of a band, it will behave like a particle with negative effective mass. And that's why the motion of electron in the top of the band is analogous to the motion of a hole. Or in other words, the electron here behaves as if it is endowed with a positive charge. So please remember it, that at the top of a band, or a band that is partially filled, the electron in the topmost levels will behave as if it is having a positive charge. And here the same thing is shown. Deep inside the band, the electron is moving clockwise, but here at the zone boundary, near the zone boundary, the electron is moving counterclockwise or anti-clockwise. So it is behaving like if it is having positive charge. And so this is the same thing. Now the electron motion is shown here. It is moving clockwise when the magnetic field points inward the phase, and this is the picture shown in the periodic zone scheme. Here the electron is going like this, and it is moving anti-clockwise. So the two motions are different. Means here particle is behaving, if it particle here is behaving with negative charge, here the particle is behaving as if it were having a positive charge. So near the top of the band, the motion is like a particle having positive charge. So we have seen, now we have the idea that we can have the electron-like motion as well as the hole-like motion in many metals. And for example, in case of polyvalent metals, we can have the we can have the particle behavior, which is a combination of both electron as well as hole behavior. So for those metals like aluminium, the hole coefficient would be given by -1 upon the electron concentration minus hole concentration times E. Therefore, we need to have the electron concentration as well as the hole concentration, and their number will decide whether the hole coefficient will be positive or negative. So based on this band theory of solids, the physicists were able to explain the anomalous behavior or anomalous anomalous sign of hole coefficient for different metals. So next we can ask, if the Fermi surface is lying in the second Brillouin zone, what is the behavior of electrons? What is the behavior of electrons in the second zone under the influence of a magnetic field? So the electron will move like this clockwise, and once it reaches here, it would be translated. It would be translated here. It will appear again here. So it will move like this. So it is moving like this. Or if the electron is here, it will move like this. Then it would be translated. It will appear here, and it will move like this. So this is the extended zone scheme. If we do the same thing in the periodic zone scheme, this is the electron orbit. This is the electron orbit, and the electron is making the cyclotron motion under the influence of this magnetic field. So this is the electron orbit in which the electron will move under the influence of magnetic field. This is electron-like behavior, and we have seen at the here, if the electron is here, it will make the hole-like behavior, and the corresponding orbit will be known as the hole orbit. Therefore, there can be a balance between the electron-like and hole-like behavior, and hence we get strange hole coefficients for polyvalent metals. So if the electron is very close to the zone boundary, you see the electron is moving like this. Once it reaches at the zone boundary, it will be Bragg reflected. So it will go and it will appear at this point. At this point, and again it will start moving. This, and when it reaches the zone boundary here, it will be reflected here, and it will start moving like this. When it reaches here, it will be reflected here, and it will start moving this. So whenever the electron reaches the zone boundary, means its wave vector is equal to half the length of the first Brillouin zone or any Brillouin zone, then it will be Bragg reflected. So with this, I conclude discussion over the Fermi surface and Brillouin zones. If you have any question, you please ask. So more questions. The topic is not so simple, my friends. You might be having some questions or doubts. If you don't have any questions, should I remove this? There are two things. Either everything is clear to you or nothing is clear to you. So you decide by yourself where you stand. Can you see the presentation?
Yes, sir.
And it is moving also?
Yes, sir.
Okay, thank you. So next thing which we would like to discuss is electron dynamics. Electron dynamics in a band. We apply electric field, then electron will move from one K point to another K point. If we apply magnetic field, the electron will do the cyclotron motion. It will move on a circular path around the Fermi surface. So it is very important to understand the electron dynamics or the electron behavior, electron motion inside a band under the influence of electromagnetic field. By now, we have seen that the electron interacts with the positive ion cores, and when we apply the external electromagnetic field, it will respond to those external forces also. Therefore, the electron will interact externally as well as internally, and its behavior would be completely different from that of a free electron. And it is very important topic in which we would like to govern many concepts, like the concept of effective mass, how we can have the how we can have the concept of effective mass and how it is going to influence the behavior of electron in a band. We will also study about in more detail about the concept of hole in a band. We will see how the velocity of electron will vary depending upon the position of electron in a band. So this is going to be a very interesting topic. It requires your attention. If you want to understand the electron dynamics in a band, then it requires your positive attention. We have so far the knowledge that when electron moves in a periodic potential, it is not a free electron, rather its wave function is a plane wave modulated by a function which has the periodicity of the underlying lattice. So we call the wave function of the electron as block wave function, and the electron itself is known as the block electron. And in the coming classes, we would also see the difference between a free electron and a block electron. The two are not same. So the motion of a free electron with momentum with p wave vector can be described by an infinitely extended plane wave e to the power ikx. If there is any free electron, the electron does not interact with the positive ion cores. So electron is free and its wave function is represented by a plane wave of the form e to the power ikx in one-dimensional case. So this is the plane wave that has been shown here, and this plane wave extends from minus infinity to plus infinity. This occupies the whole space in one dimension. Now, if we see on this plane wave that we can very well define the wavelength of this electron, because it extends from minus infinity to plus infinity, we can consider any two neighboring maxima or minima, and the distance between two maxima or minima is denoted by the wavelength. So we can very well define the wavelength of a plane wave that extends spatially from minus infinity to plus infinity. And if this wave represents a free electron, then we can ask, since the wave is extending from minus infinity to plus infinity, we have very precisely defined its wavelength, and wavelength is related to wave vector k is equal to mod k is equal to 2 pi upon lambda, and k wave vector is related to momentum. So if we very precisely have the knowledge of the wavelength of electron, then we can very precisely predict the momentum of the electron. But we ask a question, where is the electron? The wave that represents the electron extends from minus infinity to plus infinity. And the genuine question is, where is the electron? We don't know. We have the precise information about the electron momentum, but there is large uncertainty in the position of electron, and this is where we have the Heisenberg uncertainty principle. If in the opposite side, what we do, we confine or we localize the electron within an interval delta x, that our electron is somewhere in this spatial distance delta x. So now in this case we know the exact position of the electron, that electron is localized within this distance delta x. If we ask what is the momentum of the electron, we cannot tell, because we don't know what is the wavelength of this localized wave, and since we don't know exactly what is the wavelength, we cannot precisely predict the momentum of the electron. So mathematically, localization can be described by expressing the state of the electron as a wave packet. यदि आपको पता होगा, पहले तो ये सारी चीजें चल रही थी, फर्स्ट इट वाज कंसीडर्ड दैट द इलेक्ट्रॉन्स आर पार्टिकल्स, देन the theory, so first theory was that electrons are waves, then electrons are particles, then came the famous theory of de Broglie. That theory said that electron behaves as a duality. Electron remains in duality, it behaves particle as well as a wave. But then problem arises that if the electron is behaving as a wave, that wave extends from minus infinity to plus infinity. So that will give rise to uncertainty in the in the position of the electron. The answer was that if we want to represent the electron by its wave nature, then its wave must be represented by combination of several waves of slightly different lambda or k. In that case, the combination of such waves, large number of waves which are having slight mismatch between their wavelength, the combination of such waves will generate a wave packet that will define the electron. I hope you understand this concept from quantum mechanics. So electronic state can be represented as a wave packet, which is a linear combination of waves with wave vector in the interval average wave vector of electron is k, and we are considering several waves, large number of waves with wave vectors between k plus delta k by 2 to k minus delta k by 2, and the combination of such waves will represent the electron or its wave function psi x, and t would be equal to integration from k minus delta k by 2 to k plus delta k by 2 ak e to the power, this is the amplitude and this is phase, e to the power I kx minus omega t dk. The uncertainty principle or uncertainty relation for the wave packet will be that uncertainty in the product of momentum and spatial position delta p into delta x would be equal to h cross delta k into delta x, and delta k dot delta x is nothing but 1. So it is Heisenberg uncertainty principle, and the translation motion of the wave packet may be described by a group velocity. So for example, this is a wave packet. This is the wave packet that has been generated by combining large number of waves with slightly varying wave vector. So this is the wave packet that represents the electron motion, and it is nothing but the real part of the wave function, and at some particular time t is equal to 0, it is positioned at x naught. When the time elapses, this wave packet moves along positive x-axis, and when it moves, it will not only spread in space, but it will also move further. So after passing of time of t naught, the wave packet looks like this, and it has traveled a distance that is equal to v into t naught, where v is its group velocity, because it is a wave packet. It is a wave packet having different waves. Therefore, we talk in terms of group velocity that is given by Vg, and that is del omega by del k. After a passage of time 2t naught, the wave function will look like this, and it has traveled 2v t naught distance from its position at time t is equal to 0. The group velocity is the velocity of center of gravity of a spatially localized wave packet. The wave packet spreads out as a function of time and also changes its shape, as has been discussed. The translation motion of a wave packet is given by the group velocity Vg. In crystals, electrons are described by Bloch waves, which represent especially modulated in finitely extended waves with wave vector k. You know, psi k is equal to u kx e to the power I kx. To describe localized crystal electrons, it is therefore appropriate to introduce wave packets of Bloch waves. These are also known as Wannier functions. The localization in real space implies following the uncertainty principle, an uncertainty associated with the momentum of k vector. The velocity of a crystal electron in this semi-classical picture is given by the group velocity of the Bloch wave packet. This is some word I have written, semi-classical picture. So semi-classical picture means we are treating the electron as quantum mechanically, but its equation of motion, after considering it quantum mechanical particle, its electron, its equation of motion would be of the form that is given by Newton's second law. So this is semi-classical picture. It is not completely classical because we will take help from we will consider the electron to be a quantum particle, but after considering all these things, whatever the equation of motion we will get for this electron, that will be analogous to F is equal to ma, that is the Newton's law of motion. So if we consider the electron to be as a wave packet of Bloch waves, the group velocity of electron inside a band is 1 upon h cross del k e n k. Yesterday I told you that the gradient of energy with respect to k, del E over del K, it is proportional to the velocity of the electron, and here we have that relation Vg is equal to 1 upon h cross del K E n K. Here n is the band index. If we take the reduced zone scheme, then we have different bands separated from each other by an energy band. So we can have the same k value, but we need to describe in which band we are talking about. Okay, if you remember the reduced zone scheme, we have different bands, and different bands can have the same k value. Therefore, we need to have index n. We need to be very precise that we are talking the electron energy in first band, second band, or third band, or any other band. So we need to put n index, which is nothing but it represents the band where the electron is. The energy of the electron, it depends upon the wave vector and the group velocity. It is the three-dimensional case, so it can have three components along x direction, along y direction, and along z direction. A crystal electron described with an average wave vector k in the presence of external electric field gains in time delta t and additional energy. एक बैंड है हमारे पास, उसमें इलेक्ट्रॉन्स हैं. नाउ वी अप्लाई इलेक्ट्रिक फील्ड. सो what the electric field will do, the electron will start getting accelerated. So acceleration means it will gain some energy from the electric field, and how much energy it will gain in delta t time under the influence of E electric field would be given as delta E is equal to minus E electric field times Vg delta T. I hope you can understand this relation. It is very simple. Minus E and electric field times electric field will give us the force, and it is Vg into del T. So it is nothing but displacement. So force into displacement is work or energy. That's why we have this relation. But we also know that delta E is equal to, if we take the gradient of energy with respect to K and we take its dot product with the change in K, so that will give us delta E. We compare the two expressions. So del Ek dot dk is equal to minus E electric field dot Vg del T. Now we can write the expression for del K E N K. It would be H cross Vg. So in place of del K Ek, we have written H cross Vg and dot dk. So Vg and Vg would cancel out. H cross del K is equal to minus E del T, or we can write it H cross del K over del T is equal to minus E. We considered the electron to be a quantum particle, and what equation of motion we are getting from here is nothing but the rate of change of momentum is equal to the applied force. That is nothing but classical Newton's law of motion. So that's why it is a semi-classical picture. The rate of change of momentum or k wave vector of the electron is equal to the applied force. The condition for the validity of this equation is that the applied electromagnetic field must not be too large compared with the atomic fields. Otherwise, what it will do, it will knock out, if the electric field is very high, it will knock out the electrons from the band. So this equation, the last equation, enables us to write down a semi-classical equation of motion for crystal electrons in the presence of electromagnetic field with the influence of the atomic crystal field appearing only phenomenologically in the form of band structure Ek. यहाँ पे हमने इक्वेशन ऑफ मोशन जो लेके आए हैं एच क्रॉस डेल के और डेल टी इज इक्वल टू द अप्लाइड फोर्स, इस इक्वेशन को हमने कब डिराइव किया है, जब हमने लिया है ऐसा एक्सप्रेशन वेलोसिटी का एक्सप्रेशन वी हैव टेकन इन टर्म्स ऑफ द डेरिवेटिव ऑफ the gradient of energy with respect to K and Ek diagram. So the gradient we will get from the Ek diagram, and this Ek diagram is after considering the periodic potential. Therefore, here we are saying that the atomic crystal field or potential appears only phenomenologically in the band structure or in the Ek diagram, and using that we have derived the equation of motion of the electron inside the band. The rate of, now since the electron accelerates under the influence of electric field, so we would like to calculate its acceleration at any time t. That would be given by the rate of change of its velocity. So it would be equal to 1 upon h cross del over del t gradient of E and K. And after solving it, we can get, so what we can do here, we can multiply and divide it by delta K. So this equation will become 1 upon h cross del over del K gradient of energy with respect to K dot dk over dt, and we can write it 1 upon h cross del square E n K over del K square dot F external by h cross. So del K over del T is nothing but, from this equation, the right hand side represents the external force. So dk over dt would be external force divided by h cross. This is what we have written here. So the acceleration terms is this thing times the force, this thing times the force. And what is this equation? It is A is equal to F upon M. A is equal to F upon M. It is kind of that equation. So this would represent the acceleration if the quantity inside the bracket is 1 upon mass, and this represents the effective mass of the electron, which is shown by m star. A star over m represents the effective mass of the particle. Maybe it is electron or maybe it is the hole. So it is equal to h cross square divided by the second derivative of energy with respect to k. And we know from mathematics, from the knowledge of mathematics, that any second derivative of a function represents the curvature. Its curvature is represented by its second derivative. Therefore, the effective mass is proportional to inversely proportional to the curvature of the EK diagram. More is the curvature, less would be the effective mass. Lesser is the curvature, larger would be the effective mass of the electron. This is known as the dynamical effective mass because E varies with K. That's why it is known as the dynamical effective mass. In normal situations, the applied force and acceleration, they are in the same directions, but in reality, it is not always the case. The acceleration and the applied force, the external force, the electromagnetic force, they may not be in the same direction, and if they are not pointing in the same direction, means the acceleration is not in the direction of applied field. In that case, the effective mass becomes a tensor, and this equation, the relation between the field, mass and acceleration would be represented by a tensor. That would be, it will have three components, ax, y, az along x, y and z direction, and it will have a matrix with 9 components of the inverse of effective mass and times the force. So when the force and acceleration are not in the same direction, the quantity, the mass would be, the effective mass would be a tensor quantity. And it can be represented under such situation, the effective mass can be represented 1 upon m star ij is equal to 1 upon h cross square and del 2 enk divided by del ki del kj, where ij represents x, y or z directions. So overall, we have the effective mass is given by h cross square divided by del 2e upon del k square. This is very important relation. You must remember that effective mass is inversely proportional to the curvature of a curve, curvature of EK diagram. So here you see the two EK diagrams are shown. Here the curvature is large. For this curve, the curvature is very large, so it will have less effective mass. And for this curve, the curvature is small, so it will have large effective mass. If we don't consider the tensor, then EK diagram can be represented in terms of the effective mass as EK is equal to E naught plus minus h cross square divided by 2 m star kx square plus ky square plus kg square. So this is how we can plot the effective mass, velocity and energy of electron as a function of k wave vector. The topmost diagram is EK diagram, and you see under the influence of a periodic potential how the EK diagram looks like. It goes like a parabola, and that the energy gets lowered near the zone boundary. If we see the plot of energy, if we see the plot of velocity at k is equal to 0, its velocity, the velocity of the electron is 0, then it keeps on increasing, but at the point of inflection is where the slope becomes 0. This is having this parabola is upward, and here the parabola would be downward, and the point where the two curves meet is known as the point of inflection. Do you know the point of inflection from the mathematics? Do you know point of inflection?
Yes, sir. Here the second derivative becomes 0.
Yes, second derivative becomes 0. So at this point, the second derivative becomes 0, because here this curve is going up, and after this point, this curve this starts going down. So at this point, the second derivative is equal to 0. And at this point, you see, because the second derivative is 0, so effective mass would be infinite, and this is what is represented here. It goes plus infinity here if k is less than k naught, and it goes to minus infinity if k is slightly greater than k naught. That's why at this point effective mass is infinite. Now the velocity of the electron, when it moves up in the band, it increases up to this point, up to the point represented by wave vector k naught. So it is point of inflection, and after that the velocity starts decreasing. And you see the effective mass of the electron becomes negative. And at the zone boundary, the velocity at this zone boundary and in the left side, the velocity is 0. But the effective mass is still negative. So velocity 0 can be understood that now the electron has a wave vector whose length is equal to pi upon a, and it would be reflected in another direction, and the resultant of two waves, the combination of two waves, will generate a standing wave. And standing wave does not travel in space, it remains as where it is. Therefore the group velocity at the zone boundary is 0. We can represent the relation between the mass of a free electron and the effective mass of an electron inside a band by this ratio. Fk is equal to m upon m star. If we substitute the value of m star, we will get this relation: m upon h cross square del 2 E upon del k square. It measures the extent up to which an electron behaves as a free particle. If this ratio is equal to 1, mass of free electron is equal to the effective mass of electron in the band. So this means the electron is completely free. If, however, Fk is smaller than 1, we will have the effective mass of electron would be greater than m. And we have, as we have discussed in the first few classes, that there are heavy fermions also, in which the effective mass of electron could be 1,000 times the mass of a free electrons. So with this, I would like to conclude.
सर कल का क्लास इसी टाइम होगा?